Okay, so now we've looked at the operation of the DC motor. We got a good understanding of how it works, what's going on, even quantified it a little bit. And so let's take this a little bit further. In section 5.3, the title of the section is Mechanical Power and Torque. And power and torque are two of the primary characteristics that we want to explore when we're looking at DC motors. And what I think I'll do is I'm going to walk through his derivation of some of the equations that we'll use in this chapter. And I know some of you like that and like to go through that process. And I think it's worthwhile too. You know, sometimes we just get these equations sort of thrown over the wall to us, and we take them and we use them up, and that's fine. But for some of these simpler relationships, I think it's good to look at where things are coming from. Okay, so let me switch off of here, and I'm going to break this section up into two sections so we don't make it so long this time. And that is what you're seeing there is part of Saki the cat up here on the table with me. And anyway, she'll probably appear again here before we get done. Okay, so in section 5.3, he begins with going back again to equation 4.1, and what we see in 4.1, and let me move my head out of the way here, get out of the way. All right, what we see in 4.1 is this equation that we first looked at when we were talking about DC generators, and it's the armature voltage, number of conductors times the speed times the flux per pole divided by 60, and that was equation 4.1. Okay, so then he says, referring to figure 5.2, and 5.2 is this guy, okay? Referring to figure 5.2, we can see that the power delivered to the armature is going to be the product of the source voltage times the current, right? The basic power equations. So the power to the armature is the source voltage times the current that is flowing to it, because of, you know, our basic power equation, power is equal to current times voltage. And then he says, I can go into and get something else that I can work with by defining source voltage as the armature voltage plus that portion of the voltage that's dropped across the resistance in the armature. Or I could just, you know, rephrase that as E sub S is equal to the armature voltage plus current times that resistance, you know, that voltage drop. So that would give us two new equations to work with, equation 5.2 and equation 5.3. So what he does there, he says it follows that the power to the armature is equal to this, right? We know we get this, but if I can define E sub S as this, let me replace E sub S with E sub O, okay, plus I times R, and then that portion there times the current. And then what I will do is I will multiply this through, and I'll get E sub O, armature voltage, times current, right? And I'll also multiply here, and I'll get plus I squared times R. Okay, so that gave me this equation. Put this back here. So I'll have that. And so now we've defined a fourth equation in chapter 5, which we're going to give as this here. Okay, and that's pretty straightforward, I think, isn't it? And where that came from. And I like seeing that. I used to love to see the equations derived. Well, sometimes it depends. Some things I didn't really want to, but when they're that simple, I do like seeing where they come from. It helps me to understand that. But we can break this down a little bit, and there's some parts of it that we can look at And the first thing he says is that this I squared R term, got all these different colors, I should use them, right? I've got that I squared R term is the heat that's dissipated in the armature. It's resistance, current going through a resistive part of the circuit. And so it's lost in a way, but you know, you'll hear this a lot. We'll call them I squared R losses, and those are heat losses, and they are the product, or excuse me, it's the product of the current squared times the resistance. All right, heat losses. Now, what we get that, but this is the thing that he also points out to us, and he says that this thing here, this portion of the circuit, is very important because the E sub O, the armature voltage times the current, it's the electrical power that is converted into mechanical power. It is the electrical power that is converted into mechanical power. The mechanical power of the motor is therefore equal to the product of the CEMF, the counter electromotive force, multiplied by the armature current. Now, flip up there to page 99, and we're going to write down yet another equation, and we're going to just put that in equation form, what we just said. The mechanical power developed by the motor in watts is equal to the product of the armature voltage times the current. The induced voltage in the armature, or armature voltage times the current. The CEMF times the current. Okay, now we're going to go way back to chapter 3. Let me slip this up to here, and we're going to write down another equation. And I hope you remember this equation. Power of a motor is equal to the speed divided times the torque divided by 9.55. This was equation 3.5. And N, of course, is the speed of rotation. And so what he says here is if we combine 3.5, 4.1, and 5.5, what was 5.5? Oh, I didn't label that. That's this guy right here. If we combine all of those equations, we can come up with something that looks like this. Okay? You know, and then let's see, maybe we can look at this, you know, let me write them down first. Okay, so here we go. This power is equal to this. And he says that is equal to this, right? These two things are equal, and that seems pretty obvious. And so I can write that as this. Then I know that E sub O, right? E sub O all the way up here, this guy, I put that into my equation. So I'm going to have N times T divided by 9.55. And then E sub O is the Z times the Z times the flux per pole times the speed. I've still got current there as well. And all of that divided by 60. Then, if I were to go through and do a little algebra and just solve this for T, I could come up with torque is equal to the Z number times the flux per pole times the current divided by 6.28. Okay? And of course, I mean, you can go through that and you know, you can hopefully I hope we've got you schooled up on your math well enough that you can look at that and solve that for t and see that that would come out to that result. And then what that gives us, and be careful with this equation is 5.6, but in most textbooks, you won't see it labeled, and it's a very important equation for us, okay? So that's a very good equation for us to work off of, because it's going to allow us to do some really neat things as we move forward. The torque in Newton meters, Z is the number of conductors on the armature. This is the flux per pole. This is the armature current. And this is this constant that ends up taking care of the units. The exact value of 2 times pi, but it all works out. All right, let's make this part 1, and then we're going to work example 2.